Okay. I think we're live. So, okay. So you want to talk about the homework? Wait, that's the wrong screen again. I'm sorry. That's Discord. That's that. Okay. Okay, let's get this. Weird. That's just absolutely weird. It's switched again. So let me put this over here. And then I'll go back to this, and then really what I want to do is I actually want to fix display 3, because display 3 is choosing the wrong screen again. Okay. It's like swapping back and forth. Okay, so now that that's fixed. Okay, so you want to go over the homework a little bit. Okay, let's do it. Let me open up a new Inkscape. So, okay. Let's see. Which one's a good one? Right? So, maybe I should go over some facts that you're allowed to assume. I think I've basically gone over this problem in lecture before, so like G I've gone over. This one's probably a hard one. Maybe I'll even just give out the answer and kind of... I mean, obviously it's true, but the question is just why. So let's talk about maybe some of the easy ones and then maybe the hard ones and stuff like that. So like, let's start with 3n plus 2 is big O of... let's pull up maybe LaTeX. Let's see, render, mathematics, PDF. Okay. So we want to show that 3n plus 2 is in big O of n cubed. And so, okay, let's try to do that. Let's think about it. Okay, didn't like that. Let's try again. Okay, so where'd it go? There it is. So we want to show this fact, that 3n plus 2 is in big O of n cubed. So really, let's just pull up Desmos for a second, right? I think that's what it's called, right? The graphing calculator app. It's actually a pretty good one. Let's see here, graphing calculator. And so, you know, here's 3n plus 2, and then here is n cubed, right? And I guess actually we need to make this like g of n equals, yeah, they need to be functions. And so f of n equals, and they need to be functions. So, okay. So we notice here that this is actually a good example of how, no, I was just pulling it up. So this is how big O kind of works, right? Because if something is operating on like less than 2 data elements, you know, it's probably going to take one or, you know, it's going to be very small number of operations. So we don't really care so much if the set of operations here is worse for 3n than the other way. Let's make the y-axis go up to 100 so that we see better what's happening. Okay, this is good, right? Because we see that 3n plus 2 is beating it until about x equals, well, until apparently exactly 2, which I promise you I did not intend for that to be the intersection point, but it works out to be the intersection point. And so here, afterward, n cubed beats it, 3n plus 2 subsedes it, I guess, instead of supersedes, right? It is under it, right? But generally we would say that this is, if you had to pick an algorithm that either ran an n cubed time or 3n plus 2 time, obviously 3n plus 2 is better because time, you know, going up slower means that we use less time, which is good for our lives. So, okay, so graphically, right? Graphically, 3n plus 2 gets beat by n cubed by, after n is equal to 2. Okay, and so can we prove that, basically, what's the fact that you should apply in this case? The fact that you should apply in this case is that n cubed is really equal to n times n times n, and we know that 1 is less than or equal to n, therefore n is less than or equal to n squared, therefore n squared is less than or equal to n cubed. And that's what we really know. We know those 3 facts, right? And so if we can pick a constant here, the easiest way to do it is just to literally pick, say, the constant. We need that 3n plus 2 has to be less than or equal to this. And, you can be more careful. Like, technically, c equals 1 works if you pick n equals 2 as your starting n. You can also just pick c equals 5, right? Because then you know that you can just use this formula a few times and say, well, I know that 2 is less than 2n cubed, and I know that 3n is less than 3n cubed, so I know that this is all less than or equal to 5n cubed. Excessive, right? But, no reason against it, really. Right, because big O does not ask you for what the minimal n is, or minimal n or minimal c. All it says is that there must exist such a c n pair, right? So there has to be a c and an n. It doesn't say that you have to pick, you are not required to pick the best ones, right? And if you were required to pick the best ones, I think that c equals 1, n equals 2 is probably the quote-unquote best one, right? This is probably best, but, as I say, that's just my opinion. That has nothing to do with anything, right? So basically, this is all you have to do for this one. So this is why this one is a kind of easy problem, because you're just showing that, higher powers beat lower powers. Really, that's the moral of the story here is that higher powers beat lower powers. Let's look at that one. D. Yeah, you could do that one in a similar way. Yeah, C and D are mostly identical. The only difference is that the inequality goes the other direction. Yeah, you could do it nearly identically, is what I'll say. Let me not talk about D, therefore, because, D is D. Let me talk about F, right? And so F is a good one, because here, let's see if, well, let's just make, so, here's the secret, is that all logs are basically the same. And I know that, people will say, wait, that's not true. And you're right, it's not true. But up to big O, it is. And the reason why it is because there's a change of base formula for logarithms. So what we're trying to prove here is that log n is in big O of log n, right? And so I'm going to do it a different way than you can do it. So there's another identity that I think that you might actually care to use. Wonderful, I crashed the program. So let's pull Inkscape up again. So let me try to do this again. I'm sorry, it's normal buggy self. Inkscape is probably the best program I've seen for being able to do all this stuff. Unfortunately, it just has this slight instability issue that it will just rando crash sometimes. So let me. Okay. So my point here is log n is big O of log n. Okay, almost there. Here we go. So this is what I'm trying to show, right? And so the identity that we know is true, what we know is true is that log of any, well, really log of n, right? Lg of n is less than or equal to n. We know this is true for at least n is bigger than or equal to anything we really care about. So, these identities that I write down, it may only be true for, say, n is bigger than or equal to 1, n is bigger than or equal to 2, something like this. But as long as it's true in like a first few n, then you're fine. So here's a way that you could also do this problem. So here's a hint about calculus, right? If you know that f, right? If you know that f is less than or equal to, like f of n is less than or equal to g of n after a certain point, right? Then, or I guess a constant times that, so let's put a constant in there. So say you know, which one's the good one? This one's the good one, this one I'll delete. Say you know this fact, right? This is also exam review, because I'll ask you to do a few of these problems on the exam too. So say you know this fact. Then you also know this other fact, which is that f divided by g of n, right, is less than or equal to a constant c, right? Like this. You know this is true, right? And so the point is that if you know that f of n is over g of n is less than or equal to a constant c, then you know that f is big O of g. So what you can really do in a lot of cases is take the limit as n goes to infinity. And you might be asking, well, why does the limit matter? And the answer is that the definition of the limit says that for any distance away from c, there exists some constant n, big N, such that you're within epsilon of c. And so basically, within any distance of c, you can get there with this. And so this actually, the secret is that this actually gives you, this guarantees that the n will exist if you can show this limit. And so, for instance here, what you could do, if you were, brave or whatever, is you could take the limit of, say, let's just do natural logs. And I know you might be thinking, well, all logs are different. No, they're not really. So, so let's take this limit, right, of the, as n goes to infinity, of this, right? And then, of course, here, let's see. Oh, that was my, you know what? That was actually not a rendering screw-up. That was a me LaTeX coding screw-up. I didn't insert it as a subscript. So that was my bad. Okay. But how do we evaluate this limit, right? My hint is, it's the rule that everyone wants to use when you get to calculus, right? Everyone loves this rule. And, God, that's almost like a YouTube, that's like a clickbait thing. What's the one rule in calculus that everyone loves, right? It's, L'Hopital's rule. Or, I guess it depends on how you spell it. It has that O with the mark on it. Anyway, I'm not going to add it because I don't have a French language keyboard. So, but the point is that, what am I doing? Get rid of the border. There we go. So if we take L'Hopital's rule of this thing, we notice that this is an infinity over infinity, right? And so what's going to happen here is that if we take the derivative of this, we're going to get what? The derivative of the top is 1 over the natural log of n, or it's really 1 over n times the natural log of n by the chain rule, right? Because the derivative of the top, the derivative of natural log, is 1 over natural log times the derivative of natural log, which is 1 over n. So we'll get 1 over n natural log n, and then for the denominator, we will get, what will we get? We're just going to get frac 1 over n, right? And so this is the first step of L'Hopital's rule. Let's see. Doesn't look like it did. Oh, maybe it did. Oh, look, it did it right. So this is right. And then the good news is actually we're almost done here. We don't have to do any more steps of L'Hopital's rule because we can actually, we can cancel this 1 over n here with this 1 over n here and just leave the 1. And so this just turns into the natural log of n. 1 over the natural log of n goes, 1 over infinity goes to 0. And so this whole thing is just equal to 0. And so this is definitely one way to show this fact, right? So you want to say that that log n is big O of log n, and this is one way to do it. This is a valid proof. The other way to do it is probably simpler. The only reason why I wanted to show this proof is because you are allowed to use calculus here. You are allowed to do these kinds of arguments. So this is actually showing something much stronger than being big O. So what we're showing, so the thing is that basically if this, remember here, this limit has to be less than or equal to c. So 0 is really less than or equal to any constant c you pick, right? So pick c to be 1. Right, so that's the rule, is that you have to show that f of n over g of n, the limit as you go to infinity is less than or equal to your constant c. And that'll work for you. So that's basically it. You basically just show that this 0, and now, of course, the thing is that this is equal to 0. So as I say, this is way stronger than what's required for big O. Because if you did this argument with, say, like this one, and you took L'Hopital's rule of these two things, you would end up with basically, the first step of L'Hopital's rule where you have, say, one of these over the other would just end up with like 3n squared plus 10n plus 19 over 3n squared. The next step would end up with, 6n plus 10 over 6n, and then you could cancel the n's, or you could, I guess actually you can't cancel the n because you have the plus 10, so you take L'Hopital's rule one more time, and you end up with 6 divided by 6, which is equal to 1. And so that tells you here that you can actually set the constant c equal to, 1, but maybe you should set it to 2 or 1/2 or something like that. But the point is that, so that's how you get those. That's where the constants come in. But this is much stronger than just being big O. What this says is that log n is way, way slower than log n, right? So it's vastly preferable to a log n function. If you have a log function, it's vastly preferable to a log function. Let's see if we can even see the... So, okay, we need to blow this up. So let's blow this up to 5. And let's make this -1. And then let's take this out to 10,000. And then, where is log? Oh, they're both log. They're both log. That's why. Okay, here we are. So log grows really slowly, but if you notice, log looks almost flat, right? Like, here is log that's growing moderately, and then here is log, which is, it's growing in the thousandths for every, 50,000 you add on, at least in the beginning, right? So it's vastly better if you have a function that's log, right? Because it's much, much smaller than a log function. Okay, cool. So that's basically that. That's what I want to say about all this stuff. This one I would say probably use L'Hopital's rule on. This one I did, in my first Big O lecture, I did an example of how to tackle this. And I think the slide, I shouldn't say slide, the PDF or whatever from that lecture is actually up. So, you can look at that for this one. So, this one is... Okay, so this one is actually a pretty straightforward proof. Basically, what you need to do is you need to write out the definition of what it means to be big O, right? And the definition of what it means to be big O is this. It says, f of n, is big O of g of n when there exists a constant c and n, both bigger than 0, such that f of n is less than or equal to g of n, well, c times g of n, for little n bigger than big N, right? And then you would say the exact same thing, only you would say g of n is big O of h of n when they're blah, 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 there. And now the only thing that you have to do for the proof, right, so you have to write out the definition twice, and now you have to combine the definitions to make the definition work again on f and h, right? So argue, and so maybe here, instead of calling this a constant c, you would call this a constant d. You might call this a constant m. You can change the names just so that they're not actually hitting up against each other, right? So maybe that's one thing you can do in that proof. But that's really all I want to say about that proof, is just write out the definitions and then combine the definitions to make it work again. For h, that's not necessary. You don't have to take the log of them. I mean, I see that some people were doing that, I think, but it's not necessary. They're all 100% true, okay? They're all 100% true. Like, yeah, so which one do you think is not true? And I will show you that they are true. Yeah, so remember that e... Okay, so let's graph them, right? It's a good question. E to the n and n to the 10th, right? And look, come on, give me what I want. Here we are. Okay, so we need to reset our domain a little bit because I think it's going to be really hard to see. Oh God. Thank you. So you're right that it looks, if you graph it just with like a standard window and a graphing calculator, that e to the n is getting beaten by n to the 10, if you just look at it this way, right? But if we zoom out, let's zoom out further and further. Let's see, how do we do? No, actually what we have to do is we have to go up. And we have to go up, 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 up. Let's see. Actually, when are these two going to intersect, right? So that we could actually just do that calculation. When is n to the 10th going to be equal to e to the n? And the answer is... Oh yeah, no, I know I can do that, but we need to figure out the actual thing. So let's set the y equal to like 100,000. Something like that. Not even then. Let's set y even to... wait, what is this? 2 million? Here we go. There we are. So, here's e to the n. And here is n to the 10th. And you see that n to the 10th is winning. N to the 10th is winning until n is equal to 36. When both of the functions are approximately 3.4 times 10 to the 15th power. Right? So, so it's huge, right? So the y value is huge. Actually, the x value is not that big, right? The x value, or really the n value that you're looking for, is not that big. But that's the point, is, yeah, at about 36, there's another intersection point, and then you see that e to the n wins out. Now, how do you know that this has to happen? And the rule is, so I don't know if you guys have seen these rules, but basically, the rules in life... I don't know, everything looks okay from my end, but maybe there's problems. sometimes refresh your stream and it would be okay. So the rules in life are constants are less than logs. So basically, what I'm going to do is I'm going to say constants. Crap. I'll draw an arrow. Logs, linear stuff, polynomials of degree bigger than 1. Really, actually, polynomials of degree less than 1, so like square roots and stuff. And then what you end up with is above polynomials you have like exponentials, and then you'll have like factorials, which are slightly super exponential. And then finally what you're going to end up with is like super exponential stuff, which that's like the e to the n stuff. So that's how you can pretty instantly know that if I give you a polynomial, even if it's n to the 100th power, it's still going to be big O of e to the n. And the reason why is that eventually e to the n will beat any polynomial. I don't care what polynomial you write down, e to the n is going to beat it. 2 to the n is going to beat it. Even 1.1 to the n is going to beat it eventually, right? So this is stuff that, what should I say about this stuff? It's like stuff that you learn in Calc 1 and 2, right? So this is the kind of like thought process that should go into anything when you're just looking at functions. So don't look at functions and think to yourselves like, man, I have no idea. The answer is you should kind of know the answer beforehand, and this basically tells you what the answer is. Now, of course, log isn't exactly log, so technically if we were going to put logs in there, logs would be somewhere between constants and logs, right? But again, that's, this is not a complete listing of all possible functions. This is just a bare bones thing that says, like, constants are less than logs, or less than polynomials, or less than linears, or less than... Basically, this is roots. Really, I should say radical, like, powers, degree less than 1. So not polynomials, really. Polynomials are things with integer degree, usually. So linear stuff, like lines of any kind, and then polynomials of degree bigger than 1, exponentials, factorials, super exponentials, right? Factorials, there's a useful approximation for factorials, and that's called Stirling's approximation. And basically, Stirling's approximation says that, let's see, 1 over square root of 2 pi n times n to the n divided by e to the n is approximately n factorial. So, and you might think that this is like a really horrific looking thing, but the good news about Stirling's approximation, so here this is called Stirling approximation. For big O purposes, a lot of the times you can actually just ignore this part, because this is only a single square root of n power, so actually most of the time you can just completely drop that. And even most of the time you can actually ignore this part and this part. So, as it turns out, in big O, n factorial is big O of n to the n. And is it theta? I think it might even be theta of n to the n. So, or I guess it's not quite theta because it has this e to the n factor, but the point is, like, it's almost theta of just n to the n. There's just, these are little correction factors. So basically, these little correction factors can usually be like this one can be ignored first, and then sometimes you can ignore this one. This is the driver. This is the thing that actually drives the behavior. Oh, I guess that's Pac-Man again. How do I get it to be a circle again and not do that? anyway, so this is the real driver of the function. And so by the time you get to algorithms, you should definitely know Stirling's approximation. So by the time you go into 441, you should know this. Okay. So I think that's a pretty good overview, and let me just save this so that it doesn't kill itself again. So let me just go on to the other problems on the homework. And the other reason why I'm talking about these, and you might think, like, aren't you supposed to be doing exam review? The answer is I'm going to give you some of these on the exam. So this was also exam review. Okay, so for this one here, compute the time complexity of the algorithm. This one goes up to n, this one goes up to n, so they're going to go up to n times n, so n squared. And, you know, giving you the answer doesn't mean anything. I want you to tell me why. If you just write n squared, you get nothing. You have to explain why this is n squared, right? So I don't care that it's n squared. I know that it's n squared. Tell me why it's n squared. I also know why, but that's what I'm more interested in. What about this one? Oh, this one's a little tricky, right? So remember, big O is calculating how many times, it's calculating how many times this while loop is going to run, right? With a for loop, it's easy because you know this is just going to run n plus 1 times. How many times is this while loop going to run? And the answer is, let's just pretend that I is equal to 1, right? Yeah, you can set I equal to all the way up through all the other numbers, but like, let's just set I equals 1 and see what happens, right? So if I is equal to 1, what are we going to get? Right, what we're going to get is, let me actually just like print, or no, let me do a, what is this, snipping tool, so that I can snippy this thing. Okay. And then copy, paste. Okay. So what am I going to do here? So this is basically my big hint. And I'm not going to solve the whole problem, but this is what I'm going to do. And I'm basically solving the problem here. But so for this one, let's just look at how many times this while loop runs. So the first time the while loop is 1, then it's 2, then it's 4, right? Because it's doubling every time. 8, 16, 32, 64, 128, etc. All the way up to n. And so remember, 2 to the, basically, the number of steps, right, is equal to, well, I shouldn't say that. 2 to the number of steps, right, 2 to the number of times that we doubled, is approximately equal to n. That's my hint. Okay? So 2 to the number of steps is approximately equal to n. And that's all I'm going to say about that problem. So you just have to play around with these things, right? This is code, right? So you can just see what happens, right? So if n is equal to 1,000, how many times is it going to run? Well, it's going to run, 2, 4, 8, 16, 32, 64, 128, 256, 5, 12, 1,024. It's going to run about 10 times, right? It's going to run about 10 times. And as it turns out, that is approximately the something of 1,000, right? Approximately. So, and then here I give a big hint about how to count up these while loops, right? So this one is a huge, unbelievably huge hint. I mean, this is basically giving you the answer. Think of the inner loop as the Gauss sum, right? And so it's an analogy to this one, right? If this one takes about, the L word of time, right? Then what would this one take? Because the total, while the total is less than n, so how long does it take for the total to get up to n, right? We're basically adding up we're not adding up squares. What we are is we're getting to a square, right? So the number of steps is approximately well, I shouldn't say that. The square of the number of steps, that's the right way to say it. Let me quote that here. The square of the number of steps of the while loop in 5 is equal to, well, approximately. Is approximately equal to n. right? And so that's the big hint, right? So that's how to attack that problem. Okay? I think that's basically the right way to do it. I mean, yep. I think I did something like this in class, which is why I put this one on. I think I talked about an example. I hope I talked about an example like this in class previously. I didn't talk about an example like this in class precisely, but it's kind of an analogy to this. It's very similar, and also it's this is the hint for it, right? I mean, it would be whatever lecture I talked about Big O, right? I would hope. I think I talked about Big O in 2 lectures. So, I remember I definitely remember talking about it. I'm going to pull up the notes in the previous lectures. Let's see. First Big O lecture, second Big O lecture. Let's open them up. Let's see here. It's not in the second one. Let's see here. Maybe it's not in here, but then I don't remember. Oh wait, here we are. Here we are. Right here. It was in the I did talk about it, but it was kind of hidden in the quicksort analysis. It's basically the log of 2 to the number of steps is equal to this stuff. So my argument was like 2 to the number of steps is less than or equal to n, right? It's the same mathematics, right? I just simplified the algorithm, right? So here we have all of quicksort that we had to deal with, and we had 2 to the number of steps is less than or equal to n, and this is exactly what I'm basically dealing with in this other one. The only difference here is that this is literally just an algorithm that is just taking time, right? So unlike quicksort that's actually doing something, this algorithm is just taking time. So that's the only difference, right? Okay. So I was thinking I would look at maybe the exam 1s that I gave previously. So yeah, I guess that's my bad. I vaguely remembered talking about it. I knew I said 2 to the number of steps in some lecture. I just forgot exactly what context. It was kind of hidden inside of the quicksort analysis. Okay. So I think this is the exam 1 that I gave last semester. So here I just make you state the definition. I don't know if I'm probably not going to include this, so forget it. Identify and justify, right? Which ones are true or false. So here it was a little bit more dangerous, right? Because some of them can be true or false. So is 2 to the n plus n squared less than or equal to 3 to the n? The answer is this one's true. This one's true. You pick a constant. C equals, 10 or something. N is equal to 2, something like that. N squared is omega of 2 to the n. So n squared is big O of 2 to the n, because n squared is always going to, it's a polynomial, so it's always going to get beaten by an exponential. And so that's exactly the problem. So if I ask a question like this, how would you attack a big O problem that's false, right? What you could do is actually just pull out calculus again. That would be one pretty easy way to do it. You could say, pick a constant C, right? So you always have to do those things by contradiction, right? So let's write off it. Let's be more careful and just write everything down here. So let's render mathematics, and let us render that. What is it? N squared is in omega of 2 to the n. And so it's definitely it's in O of 2 to the n. That's true. but this is the other direction of the inequality, right? This is the other direction of the inequality. So this is actually false, right? I might not give false ones, but this one is false. And the reason why this one is false is because the definition of big omega is that this is, f of n is n squared, and g of n is 2 to the n. And what we require is that f of n is bigger than or equal to a constant times g of n, for some constant c, right? Technically bigger than 0. Okay, so what that means is that the limit, right, of what is it going to be? The limit of f divided by g has to be bigger than or equal to c, right? That's what that is saying. The limit as n goes to infinity of f of n divided by g of n has to be bigger than or equal to the constant c. This is the equivalent statement in terms of limits. And so this is what we're going to do is we're going to assume it's true. And then what we'll do, we'll assume it's true, right? Assume it's true. Therefore, there is a constant c, right? Okay, so given that constant c, we plug it into this limit. And so now what do we do? Now we actually have to replace these things with the actual functions, right? We can't just do f and g anymore. We need to use the actual functions. So this is n squared, and this is 2 to the n. And so what we're going to do is we're going to hit it with L'Hopital's rule a few times. So it goes to infinity over infinity, right? And so this thing is going to, here we're going to get 2n here. And then for 2 to the n, I mean, it's basically the same as e to the n, right? But except that it produces a factor of the natural log of 2, unfortunately, for the first step. So let me draw this out for you so that it's all visible. Let's hope that, unfortunately, it looks like infinities have changed into end parentheses for some reason. But let's just re-render it and hope that it fixes itself. Looks like that's fixed at least. Okay, so this is the first time you take the derivative, which is still an infinity over infinity, right? And so we do it one more time, right? And so we're going to get the limit of 2, right, over, and then the derivative of this is actually the natural log of 2 squared, unfortunately. But it doesn't matter. All of that is just a constant, so it's never going to matter. It's just going to die out in the end. And so the thing is that this is equal to basically 2 over infinity, right? Like this, right? So let's draw that out. So you're going to end up with this equation, the limit as, okay, it didn't render the n that time. Let's try it again while we wait. So here, n goes to infinity. This is the natural log squared. Oh, it didn't render the 2 to the n either. It had 2 issues when it rendered. Let's see. Here it didn't render anything. Let's try one more time. That looks right. Let's take this one. So the thing is that this is 2 over infinity, right? Well, to my knowledge, 2 over infinity is just 0. Right? So that's basically what we're going to say. 2 over infinity is just 0. So 0 cannot be, right? So this is false, right? So now what we know is that this statement here is false because, right, false because c is bigger than 0. That's the only rule for c, right? And what I'm telling you is that 0 is bigger than or equal to c, which is also bigger than 0, right? So that's not possible, right? Because we've sandwiched c in between 0 and 0, but here there's not even an equal sign here, right? The rule is that c has to be bigger than 0. Here it is. And then we've also proven that 0 has to be bigger than or equal to c. So So that's just not possible. So basically, what this tells us, right, is when we go back to or CMSC 203, right, tells us that this is a contradiction, right? And so the answer is that we broke something. And so what did we break, right? Well, we only made one assumption, right? The only assumption we made is, therefore there is assume it's true, therefore there is a constant c. So we assumed that the constant c existed, right? That there was some number for which this worked. And so hopefully that's probably what broke. So c doesn't exist. And so if c doesn't exist, then it's not big O, or big O, in this case, big omega, right? So this is the proof that you would have to write. Basically, you just do some algebra, really this is calculus, I guess, and that's what you do. All right. So you don't have to write all of this. Really, the mathematician, all you have to write is contradiction. Therefore, n squared is not omega of 2 to the n, right? You don't have to tell me that all of this stuff, all this extra stuff, but what you do have to tell me is that this is a contradiction, right? And that c doesn't exist, right? And therefore it's not omega. So that's an example of something on the test. So let's get away from big O and actually do other things, because there are other things. So let's go into what the rest of the exam is going to look like. So this is an example of a problem from a previous exam. And so basically here you just have like a stack that you push some stuff and you pop some stuff. So let me actually snip it so that we can do this problem in right, okay. In Inkscape. So let's do this problem. So here's the stack, right? s.push5. So basically what we do is you just have to keep track of the stack, right? So here's 5. And then we are going to push on, whoops. Let's put the problem here so that I don't accidentally do this. So then what we're going to do is we're going to push on 7, like this. And then we will push on 12, right? And then what we're going to do is, I guess we're going to pop, right? And I see out s.pop. So what prints out, the first thing that's going to print out is 12, right? And then we delete this node. So actually I'm going to keep this one, and I'm going to say this is like step 1, right? Step 1 is this, and then I'm going to copy paste it, and we'll just start from here. So we'll just say this is now this. And so now we're going to push on 15, right? Push on 15. Push on 72. Right, the numbers are totally irrelevant, except for the fact that they're what prints out, right? There's no structure to the numbers. They're just identifiers. Okay, and then we pop twice, right? So then we pop twice, so then 31 gets popped off first. So maybe I'll shift this over and we'll keep both of these stacks, right? So then what happens is that you pop twice, so let's delete those. What pops, 31 prints out first, right? So 31. I guess actually I put n lines here, so it's 31, 72. I really don't care about the n lines. The whole point is just what gets pushed and popped. And then we push on 13. But you notice that 13 never gets printed, it never gets popped, so it goes onto the stack, right? And that's it, right? So this is what prints out, 12, 31, 72, right? And then what is the state of the stack? Draw out the stack indicating the bottom of the top. So basically, all you really have to do is this, but it'd be nice if you included your other diagrams. Just put these all here, and you can be like, this one's the current stack, right? These are all working, this is just, this is like show your work. And then you say, this one is the top of the current stack. And that's all you have to really do for this problem, right? You just have to say, here's the top of the stack. I can figure out which side is the bottom. If you say this is the bottom, I know the other side's the top. Just the only reason why I do that is because technically you could start the stack at the top and you could go down, right? So if you ended up with something like this, where you had it the other direction, that's totally legal. There's nothing here that prevents you from doing it. It's just that then basically the top of the stack is actually the bottom of your diagram. So then this would be the top of the stack, and this would be the bottom, right? So I don't care which direction you draw it out in, as I say. That's why I make you label the top and the bottom of the stack, because it's possible that you say, oh, okay, the stack is going up this way, so, you know, or it's possible that you say the opposite, which is the stack is going this way, right? And let's see. Something like this, right? So that's basically the point there for that question. You know, it's just a do you agree that we both know what a stack is, and is that okay? These questions are basically the same. I would not give you this question again, just because I haven't done exactly an example of it. Maybe I'll just do this example now. It's a good question. I'll just do it as an example. The other ones are pretty simple, I think, right? Let's look at the other ones before I just skip them. This one looks to me, right. So this one is saying, while I is less than number, right, and we're dividing number by 2, and we count up. So the inner loop is an O of n operation where n is the number, right? So the inner loop is O of n. And what is the outer loop? The outer loop, how many times does this run? So this runs while number dividing by 2. So if number is equal to, say, 16, right, it's going to be 8, 4, 2, 1, 0. So it's basically, the outer loop here is going to run log times. So the total thing here is going to be log n times n, so it's going to be O of n log n. And that's what this is. This is a weird function, or I should say a weird bit of code, because normally, well, I shouldn't say that. It's fine. Nothing too odd about it. The only thing to realize here is that it doesn't care that the number is like counting up each time to like this is technically counting up to something that's like a square, but you don't care about that because each one of these is really just an O of n operation. It doesn't matter that you're adding on I each time, right? This is O of 1. This whole loop is O of n. This outer loop is log n times whatever the inner loop is, which is O of n. So it's O of n log n. And then here, I think this is just a straight up n squared algorithm, right? It's actually slightly better than that because it's kind of triangular, right? Because this goes from 0 to n, and this just goes from I to n, or I plus 1 to n. And so this is actually just... It's really adding up triangular numbers, but the triangular numbers are also squares, yeah. So basically, the way to attack this problem for B is to set up a summation, and you basically just prove that that summation is equal to the sum of all integers between 1 and n. Okay, so for this problem is a different one, and I haven't shown you any examples like this. I did show, trust me, I showed them an example like this in the previous class. So this is a recursive function here, and so basically you have to like build a sequence. You know what? I'm gonna say never mind. I mean, it's O of 3 to the n is the secret. But I don't really care to prove it, and I'm not going to ask anything like this on the exam. I forget exactly how I told them to do it, because I'm thinking of setting up a time of n is equal to t of n minus 1 plus t of n minus 2 plus t of n minus 3 type of sequence, and then t of n is, and then, well, t of n minus 1 is equal to, you know, t of n minus 2, so it's actually what? 2 times t of n minus 2 plus t of n minus 3 plus t of n minus 4, and then, you know, this is equal to what? If you get rid of this, it's actually equal to, like, 4 times this plus, what, 2 times this plus 2 times t n minus 5 or something like that. And in the end, what you will say is that when this gets down, so you see that it's actually kind of doubling. So you can kind of see that the time is going to be exponential because it's sort of doubling each time you do this trick. And so sort of doubling, but then the problem is there's 3 of them, so it's going to end up being O of 3 at the end. But I'm not 100% sure what kind of argument I required last time, and so I don't want to require this problem because I think it might be hard. So here I say implement a linked list node. So here you basically, this one's pretty easy. All you got to do is say that there's a next pointer, so you do like a, you know, list node pointer, right? So in order to do this problem, let's see here. Let's copy it, paste it into here. So, you know, what do? Basically, all you'd have to do is this. You'd say list node pointer next, right? And say int data, right? Or you could even say string data or whatever, right? So I don't care about what the data is, but I guess I didn't actually say what the data was, but it doesn't matter, right? So here's, let's see, implement a linked list node and then reverse. Okay. So this is actually a good problem to think through of just how to reverse a linked list, right? It's like a coding problem that you see on a lot of, what should I say? You see it on a lot of like hiring stuff, and what I mean by that is like whiteboarding interviews. When you go to get a CS job, they'll ask you this kind of almost literally a question like this sometimes. It's just how to reverse a linked list or something like that. So it's always good. The thing is that sometimes people don't ever actually get any practice to do these little gimmicky things. And so, you know, you'll go into the coding interview and then you'll be like, oh, actually, I just need to know how to like reverse a linked list. So, you know, okay, I was stupid. I should have done this differently. Instead of doing this, I will delete all of these and just stop grabbing it. Copy, paste. I think I need to just move. See, I did it again. I need to move this far and away. So how do you reverse a linked list, right? How do you do it? I think this is enough nodes to see, right? Basically, the point is what you're going to have to do is you need to get this next, right? Needs to actually point back here, right? And so how are we going to do that, right? Whoops, that's not right. There we go. So how do we get a linked list to reverse? And the answer is basically what you have to do is you need to do some, if we have like a p current, whoops, right? Let's say we have a linked node pointer p current is equal to the head, and let's say that we have a linked node pointer p next is equal to p current dot next. And so how do we reverse it? It's pretty easy. All you have to do is say p next, right? Or if p next, right? Because it could be null. Crap. Have to use spaces, cannot use tabs. So if p next, then what we're going to do is set p next dot next is equal to the p current, right? But then what's the problem, right? What's the problem? The problem is that then we have forgotten, we just forgot about the original next, right? So what we've done here is we've deleted this connection. And so we've set this now. And so basically the first thing we're going to do is so before we do any of this, we should probably set, head dot next equal to null pointer, right? To get rid of this connection here. And so now this is set correctly, but now we've forgotten about that. So how do we avoid forgetting? We avoid forgetting by remembering. So we'll have another link node, right? Link node, and we'll call this p old, right? And so this is going to be equal to what is it equal, or let's just call it, what is it? Next or something like that is equal to p current dot next, right? And so that what we're going to do here is that what we need to do is we need to make sure that this is always updated. So if p next, then p next, right, is equal to p current, or let's just say p next dot p next. So that's all we have to do. So we can actually get rid of this. We can just say that this is, there we go, done. And so that's how we prevent forgetting. And then what we're going to do is we're going to say, okay, now what we're going to do is we're going to set p next equal to p next, and probably set p current equal to p next. And what this is going to do is going to get us ready for the next step. And so what I mean by that is now, instead of this one being the current, right, and this one being the next, and this one being the next, we're going to move everything up by one, like this. So now this is the current, this is the next, and this is the next. And so now it's going to set next pointer, it's going to set it to here, and then that'll get rid of this one, this arrow. But the good news is we haven't forgotten about this one because next is set. And so then we'll just keep advancing. So instead of an if statement, actually this is basically done. The only thing you need to do is do a while, right? While p next. And that's it. That's really it. I imagine here we would set head.next equal null pointer probably here maybe, so that we wouldn't accidentally, right? And the reason why we want to set head.next equal the null pointer is because so we want this thing to point backwards, right? So this thing points backwards into nothing, right? So we want this to be, whoops. Yeah, so since this points back into nothing, we actually want this to be null pointer. So, I don't know if this is 100% fixed up or if it's perfectly right, but this is basically the idea of how to do this type of problem, okay? So in this case, you need to keep track of, like, yes, 3 nodes, because to reverse a linked list, you need to know the current one where you're going to set the next pointer to, the next one where you're going to, from which the next pointer will be set, and the next so we don't forget, right? So I think that's why we need 3. Maybe you can do it with less if you're creative or something. You could do, well, but no, you really can't. I think maybe you need 3. Maybe you need 3. But this is just an example with 3 pointers. There's nothing wrong with 3 pointers, right? It's just, for example. So this is kind of what you would do for this thing. And, technically this should be like node reference, so that at the very, like, reference pointer or something like that, so that at the very end, whatever the p current is, we set, head equals to p current or something like that. And that's what we do. Okay? So I think that's a slight mistake in the actual problem, but the good news is I didn't exactly grade for that, so it doesn't matter. Okay, so let's keep going. Let's look at more problems on this exam that I gave. Here's a binary search tree. Draw out a binary search tree where we insert the following elements, and then the next one is a delete. And then I think this one might be the last problem that we'll do. Yep. Nope. Let's see. Oh, implement the insertion algorithm. Cool. And then I'm just skimming through to see what is the best case. I'm not going to ask you this yet. Or maybe I would. Maybe this is not a terrible question. This isn't a terrible question. Question 12 is not going to be on your exam just because I haven't finished AVL trees. We'll do AVL again the day we come back from spring, or I guess Tuesday when we come back from spring break. So we did AVLs a little bit. So AVLs have been covered, but I think I'd rather do one more day on AVLs before I actually have you working on AVL trees on an exam. I think that's... Okay, so let's copy paste this problem. Let's see, where is my snipping tool? Let's snip it. And then let us paste it into here. Oh man, that is small. Whatever. Okay. Okay, so here's the thing. Let's draw out a binary search tree where we insert the elements in the following order. So I'm going to do this fairly quickly unless I screw up, and then I'll do it a little slower. I know that... there we go. Perfect. So... and it's still a little messed up. I think we just have to, like, unify them somehow. Okay. Okay, there we go. Now I think the circle should be fixed. There we go. All right, so 53 becomes the root because it's the first thing we insert, so let's put that in as 53. And then the next thing we're going to do is insert 21, which is less, so then it goes over here. All right, so 21 goes here. Can I do this? Yes, 21. And I'll draw in the arrows in just a second, once it becomes complicated enough to need them. And then here is 18. Right, 18 on the left. And then 72 goes over here on the right. And then 91 goes here, right? 91. And then what? 62. So 62 is bigger than 53 and less than that. So that is the child here, right? It's the left child or the right child, so 62. And then let's do 87. What happens to 87? So 87, it will get inserted here, and it goes right, and it goes left. So I think at this point I should start drawing in some of the arrows. Let's draw in some arrows now. Here, or at least lines that connect all the things, because this one, you might think it's the right child or something of this left child node here, but it's not. Okay, and then 19, what happens to 19? 19 goes here, because 19 is what? It's less than 53, less than 21, bigger than 18, so it goes right. And so 19 goes there. 108. 108, it's the biggest thing, so it goes all the way to the right. 108. Yep. So I think we're almost done, right? So now we have 12, which is the smallest thing in tree, so it goes all the way left. 12. And then what? 5. So 5 is, again, the smallest thing in the tree, so it goes all the way left like this. And then what? 72, or no, 17. is less than that. Okay, so it's bigger than 12, less than 18, so it goes here. Should have really just copied something that's easier. Okay. And then 32 is less, but then greater. Okay. Right, so this is just what you do, right? 32. And then finally 44. 44 is, unfortunately, I've drawn the tree moderately well until this point. We're going to have to do a little bit of, cheating at this point. We're just going to have to stick 44 in here, and it's going to look a little ugly. Unfortunately, this is just the way it is. It's the right child here, and unfortunately, it's starting to bodge into the right subtree over here. But whatever. I mean, as long as you connect up all the lines, it's pretty obvious what's going on. So that's it. Draw out a binary search tree where you insert the elements. Done. Right? Okay. Let's see. Where is it? Here it is. So let's delete. Why is it so small? Let's make it big. There we go. From the following tree, delete 12. So we're going to try to delete 12, which is right here, right? And so remember what we're going to have to do, right? So what's the rule for deletion? The rule for deletion is find the node. We did. And then you have to find the successor, right? So what is the successor? The successor, remember, is the least node on the right side. So you go right once, and then you go left as much as you can. So this is the successor node here. And so how would you delete this node? The answer to me is this. What you would do is I would probably draw, an X over this node to indicate that it's gone. And then what I would do is maybe either draw an arrow or just maybe scratch out this node and then write in 13 replaces 12. And that's it. That's how you delete that node, right? And that's all you got to do, okay? And so the reason why 13 replaces 12, remember, is because once you find the successor, you copy the successor's value, right? Copy the value. And then you actually delete the successor node, right? So you're deleting the actual node's value, but you're deleting the successor node itself, right? Not just the value. Because you've already copied the value from the successor up to wherever it goes in the tree, and that's basically that. Okay? So that's how to do that problem. Not so bad, I think. Not so bad. Recall, use the tree in number 7, write out the pre-order traversal. This is definitely going to go on the exam. And I can't promise you whether it's going to be a pre-order traversal, a post-order traversal. Some kind of traversal of a tree is going to go on the exam, just based on the absolute amount of nonsense that happens when people, when I ask people to do it on the exam. So let's do a pre-order traversal. And also, you need it for your project. You need to understand traversals for your project. So we're just going to do this before the deletion. So pretend that these scratch outs aren't there, right? So let's just take another copy of this tree. Let's just take another copy so that we're not looking at all the scratch out stuff. Okay, there we go. I know why it's small. I know why it's small. It's because I'm not zooming in. See, now I'm smart. I'm zooming in like this, and then if I copy this, it'll be big when I paste it, because it's dependent. It doesn't scale. It's 100% dependent on the size, the actual bitmap size. So let's do this and then paste. See? That worked. All right, so let's do a pre-order traversal of this tree and see how it's going to ship out, whatever. I wanted to say shape up, but then I didn't say either of those things. Okay, so remember, a pre-order traversal visits node, then left subtree, then right subtree. Right, so that's the step for a pre-order traversal. You visit the node, then you visit the left, then you visit the right. So first you're going to visit the node itself, which is 35. Then we're going to visit the left subtree, which is at 12. The left subtree is going to, so now we're at 12. We're going to visit 12, and we're going to go left. So then we visit 8, and we go left. And now we'll visit 7. So now 7 tries to visit left, can't, right, can't. So it pops back up to 8. And so now it visits from 8, right? So here was 8 that visits left first, and then we visit right. So visiting right is going to be 10, and then 11. Okay. And then what do we do next? Right, we pop up, and then we'll be at 12. So then once we get back to 12, we go right. So then we visit the node, 16. Then we visit left, 13, visit right, 22, and then we'll visit 27. Now, here's the thing to realize. We don't visit 22, 27 because we visit this node, and then we visit, like, we don't visit 16 left, right, and then we visit the children, right? If this had a child, we would have visited it first, which is usually the mistake that people were making. Okay, and then finally we pop all the way back up to here, and here we do 44, 37, 48. Okay, so that's it. And so if you're going to do a post-order traversal, it's really the opposite, post-order traversal. It's the same as an pre-order traversal, except you do left, right, node, right? So instead of being node, left, right, you do left, right, node. So let's think about how left, right, node is going to work. So left, right, node, what it does is it says go left, go left, go left, right? Now this node can't visit left or right, so we print out 7, and then we return up to here. Then remember, we don't visit this node, right? It's left, right, node. So we went left, we go right. So we're going to go 10, but we're not going to visit 10 because we can go left. Nope, can go right. Yep. 11, and then we're going to get 10, right? Because we pop back up. And then finally we get 8, right? And the reason is because we did the left side, we did the right side, and now we do 8. So, and then what do? Then we pop back up to here, and you might be tempted to type 12. Don't type 12, right? We go right first. We say 16, and then we go left, so we're going to say 13. And then we pop back up to 16. You might be tempted to say 16, but don't. You go down right, you say 22, 27, and then 27, 22, right? Because we're going to go right, right, and then this node doesn't have children, so you print out 27. Then you print out 22. Then you print out 16. And then finally, now that we've gone left and right, we can print out 12. And then here, are we going to print out 35? The answer is no. We don't print out 35. We go right. But do we print out 44? No. We go left. We print out 37. Then we return up to 44. Do we print out 44? No. We go right. Print out 48. Then finally return for the last time to 44. We print out 44, and then 35. Right? So now you'd be tempted to say, shouldn't the pre-order traversal and post-order traversal just be the opposite order of things? And the answer is not quite. Right? They're different. Right? They're different. And remember, it's not possible to reconstruct a tree, so it's not always possible to reconstruct a tree just from the traversals, right? And that's definitely true with the in-order traversal, right? An in-order traversal is literally just the elements in order because it goes left node right, right? So in order is left node right, and so that would just be 7, 8, 10, 11, 12, 13, 16, 22, 27, 35, 40, 37, 44, 48. And so is it possible to reconstruct the tree from the in-order traversal? The answer is absolutely not. From the in-order traversal, you can't even tell what the root is. Right? And then the only exception to that is that if you put parentheses on, right? If you put proper parentheses on all this stuff, then you can tell again, right? So if you put some like parentheses to denote that this was the left tree, this was the right side, and then this is the root of the right side, so you'll put maybe parentheses on this, right? And so that can tell you the structure. This will tell you the structure, but you notice that this is actually just re-encoding the binary search tree in this way. So basically this is what you would get here, and then 12 is the parent, so we need another set of parens around here. And then we're going to have paren, end. I think that's right. So with the parentheses you can tell. But you see that the parentheses are giving you information that the traversal itself wasn't giving you, right? The parentheses are, I mean, if you have your traversal print out the parentheses, then obviously it's giving you that information. But what I mean is that if you're just given the numbers and you're not given like how many opens and closed parentheses at every time, then you can't tell necessarily, especially from the in-order traversal, but really from any of them, the actual structure of the tree. From the pre-order traversal, all you really know is that this is the root, right? So this is the root, so clearly all of this has to be on the left side, and all of this has to be on the right side. So let's see, I think oh wait, wow, we're way past class. Ha, we're way past. Okay. Okay, let me look at the exam and see if there's anything else I want to talk about. I won't give this specific induction problem again, but this is a good induction problem. I think I've done this one in class, so it's a good problem. And then on this exam, the only thing I'll say, I haven't gone over anything on this exam, except to say that it's very similar, right? Very similar, except it gets up to, I think, splay tree, you don't know anything about that. So unfortunately, basically, this exam, you only go up to question 6, maybe question 7. So that's what to go up to. So do not go up past question 7 on this exam if you're using them as study material. I will release the exam today at some point, and it will not be due next week because it's spring break, so it's going to be due on the 25th. Okay, so the exam will be due on the 25th. Of, I guess, what month is this? March. So you'll have 2 weeks to do it. Alright, so that's it for today. I think I'll let everyone go at this point. Okay, so that was the exam review. I didn't cover AVL trees at all, so I'll take AVL trees off of this. We'll do AVL trees again once we get back. So once we get back, AVL again. There is a possibility, Dr. Johnson and I, he suggested, and he kind of seems to want to, so we'll see if it happens. Maybe there will be, may do a project-specific lecture tomorrow together for both sets of classes. Granted, I already kind of did a project lecture because I spent an entire day on Discord trees, and so that's kind of a project lecture, but he wants to do one, so I might join him on that. And if I do, then you guys will get the link, and you will be able to watch it, so that's that. It'll also be on YouTube. Alright, so I'll post the exam review. You can kind of look it over, but I'll give out the exam for the rest of the stuff. Yeah. Yeah, I'll post these notes. The prior exams are already posted, so you had a few days to look at them. Really, I think that it's important. It's good to just give people a sense of the style of the exam, and you notice that I think the exams are. The only problem with exams is that in the era of COVID, online they're kind of useless, but I have to give them. So I guess I don't have to give them, but I should give them. So that I'm trying to make the exams as useful as possible while also not being. Anyway, it's difficult. So, okay. Alright, I am saving it to PDF now. I will post it to Discord, and that's the end of the lecture. Alright. Where are you, OBS? Where are you? Goodbye, everyone.